Welcome everyone. You already know who I am, so I'll jump straight to the talk. So there has been a lot of talks about Akka Streams during this conference. I'm also a happy Akka Streams user, but I wanted to show you that there is life beyond Akka Streams when it comes to reactive stream processing as well. So today we are going to talk about Monix, and I'll start with a quick recap what reactive stream processing actually is, then give you a quick description what Monix is, then describe the simple use case that we are going to cover today, and the main part of this talk is going to be the live coding. So when it comes to stream processing, I would say that most of you these days should be familiar with what stream processing looks like in general. So you have a source of your data that you need to process. It's a producer. We can generally call it like that. We have a consumer, so this is the place where our data ends up. And we have a number of stages and intermediate stages when we are processing the data. And of course, we have the data flowing from the producer through the stages to the consumer. And now when you think about such a pipeline, there are some things that can go wrong. And the case when they can go wrong is when the producer is faster than the consumer, so or the previous stage is faster than the subsequent stage, because then there is some excessive data that the next stage has to somehow deal with. And there are of course there's a number of ways of dealing with such excess data. For example, if you look at some lower level stacks like the network hardware stack, the excessive data can just be dropped. Then you can think of a blocking scenario when the data is not dropped because, well, after all, you may want to process all the data and don't drop anything. And in a blocking scenario, basically, the slower component can just do its work and just block the faster component and then only accept the next data when it's done processing the previous one. But the idea of reactive stream processing, because this is like stream processing in general, and reactive stream processing is about non-blocking, and this is about a way for the slower part to tell the faster part how much data it can process at the moment. So the key idea in reactive stream processing is called back pressure. And it's important that it's a non-blocking back pressure. So basically, it's a non-blocking way for the slower component to request data from the faster one. So only when the slower one is done processing the data, it tells the faster one how much data it's able to send to it. So once again, we can achieve back pressure in a number of ways, in a blocking way, but in reactive streams, reactive stream processing, it's about non-blocking. So this is the general idea and general naming for stream processing. Every implementation of reactive streams, it turns out, has its own names for that. So in Monix, the producer is called an observable, so it's the source from where the data comes. Then the consumer is consumer. This is pretty straightforward. And the intermediate stages are called transformers. So they do any intermediate processing that you need. So this is like a single slide on reactive stream processing, what it's all about. So then what is Monix? Monix describes itself as a library for an asynchronous and event-driven programs. And it includes a number of useful concepts. The first one is a task. So task is basically like the Scala future, but the main difference is that this is lazy. So in Scala, when you define a future, it's executed immediately. A thread is started, the computation is done. It is asynchronous, but it's eager. A task is also asynchronous, but it's lazy. So the next concept is something called coeval. And well, the name may seem strange. Coeval is basically something, a lazy computation, but a synchronous one, so the one that happens instantly. So you can think of coeval as of a lazy val, for example, or as a by-name parameter to a function. But this is like lifted or brought to the type level. So you have a type representing a lazy computation that is happening instantly. And actually, coeval means that it's going like it's synchronous, but it has this co prefix, which is like pretty often found in the functional programming stuff. And last but not least, we have observables, which is actually the implementation of the Reactive Streams manifesto done by Monix. And this is what we are going to talk about today. So that was Monix, and this is our use case. In our use case, like what we're going to do is to import files into Cassandra, doing some intermediate processing, and going into details. In our files, we're going to have a number of lines that each of them contains an ID and a value. And for every ID, there are 2 lines. and any of them can have either a valid value or an invalid one. And what we are going to do is try to compute an average of every 2 lines with the same ID. If we are not able to compute the average because the values are invalid, then we're going to use some dummy one, but we want to do some, like not only the happy path. Then we go, so the intermediate computation is going to be this averaging, and then we're storing the data to Cassandra. And the files are going to be gzipped. Okay, so that was it for the theoretical introduction. Let's see the code now. Okay, so here is some, like the class we are going to start with. Here's some boilerplate for parsing the line. This actually doesn't have anything to do with reactive processing, so I just left it here. I didn't want to code it, leave. So this is basically splitting the line by a semicolon and then extracting the value into our domain model. Our domain model is a reading, and it's an ADT which has two case classes, for a valid one and for an invalid one. Every reading has an ID, and the valid one, apart from an ID, has a value. So what this does is basically parse every line from a file into our domain model, and that's it. So the next thing, well, the first thing we're going to do is to load the data from the files. And what we are going to do basically is to implement like some small building blocks that we are then going to combine into the full processing pipeline. All the blocks that we are going to define are going to be lazy, so they don't do anything by themselves until they are explicitly executed. So let's start with the first transformer, actually, because we'll be defining transformers here. And as you can see here, transformer in Monix is nothing more than a type alias for a function that converts an observable of type A into an observable of type B. So this is pretty simple. You just define functions. So our input type here is going to be a file, the Java IO file, and the output type is going to be the reading, so any one. So it can be either the valid one or the invalid one. So since we don't want to load the entire files into memory, because, well, we're in a streaming environment anyway, so what we are going to do is to create an observable for every file, so that we can stream the data from the file, and then we're going to transform it. So here, the underscore means that we are starting with an observable of file. Then for every file, we want to create another observable, which will take data from the file, and then we want to flatten all those observables from a number of files into a single observable. So since we want to map a file into an observable and then flatten it, we're going to use flatmap, which is the ultimate tool for many tasks. So we're starting with a file here. And then there is some boilerplate for creating all those readers, because we need a reader that we can supply to Monix. So there is this number of wrappers that you need to use to create a buffered reader from a zip file, but ultimately we have one. And now what we are going to do is to create an observable. We have a factory method that takes a reader. That's why we created one just before. And now it may happen that, for example, the file contains a header line with column names, and we may want to skip it. So we have a configuration parameter that says how many lines we want to skip from the beginning. So we are going to use the drop method to drop a number of lines. And then we want to asynchronously execute the method defined above, the parseLine1, which is asynchronous. It returns the Monix task. So we have a map task method that just takes actually takes the exact signature that we have in our parseLine method. So we can just pass it here. Okay, so this is the first transformer that we implemented. Once again, what it does, it's having an observable of files. It takes every file, creates another observable for every file, and then flattens each of all the observables created from the files into a single one that is passed downstream. And we do some intermediate computations here, like dropping the lines or doing the asynchronous parsing of each line into our domain model. So the next step is computing the average. So this is once again going to be a transformer. And this time we're going to transform from readings into valid readings, because we can take anything, either a valid reading or an invalid one, but as an output we always want to have a valid reading with an ID and a value so that we can further store it into our database. So this is a transformer from a reading to a valid reading. And so here we start with an observable of readings. So the first thing, since we want to compute an average, is going to group them into groups of 2. For this, we have a method called buffer tumbling. This may not be the most intuitive name for a method that groups into groups of an arbitrary size, but still, that's the name. And then we are going to map this asynchronously with some logic for computing the average. So now you may think, why didn't we use the map async also here for calling our parseLine method? And the reason is that the built-in map async in Monix is unordered. So it launches a number of computations in parallel, and then it emits the result downstream as soon as the result is ready. So it may break the order of the results compared to the order of incoming data. And that's like when computing the average, we are okay with that because it doesn't matter what the order of the readings stored into the database is. But here, when parsing the data from our files, we really care about the order because we need the same IDs, lines containing the same ID, to be next to each other. So we'll look into it later, how we could try to parallelize that, but we unfortunately cannot use any built-in transformation from Monix. So the map async takes 2 parameters. First is the parallelism level. So this is the number of computations that are going to happen in parallel. We have a configuration parameter for non-IO parallelism, so for all the computations that happen in memory. And the second parameter is a function that takes the element and then returns a task. So returns a description of an async computation. So we're going to have readings here. Just to remind you, we just group the readings into groups of 2. So the readings here will be a sequence of 2 readings. And what we are going to do here is return a task, since we describe an async computation that is going to happen inside map async. And now the first thing we need to do is to extract only valid readings from the collection of 2 that we have. So we're going to use collect, do a simple pattern matching here, and then store it in a variable, in a val actually. And this is actually it's going to be valid readings. And now, having the valid readings, we're going to apply some dummy way of computing the average. It may not be the most efficient one, but it's sufficient for our needs. So to compute the average, we basically check if the valid readings are not empty. If they are not, we extract the values. As you remember, the valid reading representation has a value. Then we take the sum, and then we just divide by the size of the valid readings. So we don't have any specific like case for the situation when there is a single valid reading. We just do it in a generic way. And if none of the readings are valid, we just return a dummy value of -1. So and the last thing we need to do here is to return a valid reading, because what we are writing now is a transformer whose output type is the valid reading. So we just say valid reading here, and for a valid reading we need an ID. Now we benefit from the fact that in our domain model we represent even an invalid reading by a case class that has an ID. So actually we are safe to take just the first value from the sequence of readings, because even if it's an invalid one, it's still going to have an ID. So we just take an ID and take the average. And this is the second transformer we created. Once again, what it does, it uses the buffer tumbling to group the readings into groups of 2. And then for every pair of readings, it launches an async computation described by the task here that just computes the average. So now, sometimes you may want to combine some the smallest building blocks, like those 2 here, into a bigger one, so that it can be reused, and so that you don't have to repeat the 2 of them every time. So I'll just show how you can do it. It's pretty simple. We can call this transformer process single file. And this is going to be a transformer from a file to a valid reading. So the first one, the parse file, was transforming from a file to a reading. Then compute average was transforming from a reading to a valid reading. And when we combine them, they transform from a file to a valid reading. And this is pretty straightforward because we just use the transform method on an observable, and we can provide the transformer here. So the first one we provide is parse file, and then we provide the second one, which is compute average. So this is a pretty simple way to combine a number of smaller building blocks into a single bigger one that can be reused later. So up to now, we have defined the intermediate processing stages of our pipeline. What we need for it to be complete is the source of data and the source observable and the consumer. So we'll start from the end. We'll start by implementing the consumer. It's going to be called store readings. And now it's not a transformer anymore because this is the endpoint of the pipeline. So its type is a consumer. And we need an input type and some kind of output that it's going to perhaps return when the pipeline finishes. So our input type is going to be a valid reading. And for the output, we'll just use unit because actually we don't care about the output since the values go to the database. So we only care about the fact that the computation finishes. But we actually discard some results that are coming from the database, like the representation of writes to the database. And this is going to be pretty simple because we have a number of built-in consumers. And there is one that is called for each parallel async, which basically means that it takes everything that comes and asynchronously launches a computation for every element with a given level of parallelism. So this is no more an in-memory operation, so we need a different parallelism level for writing to the database, and actually we have a config parameter for that. It's called concurrent writes. And then for every reading, we want to asynchronously store it into the database. So we have some reading repository that has some save method. We're not going to dig into details here. The only thing you need to know is that it takes a valid reading and returns a task of unit. So this is basically an async computation whose result we discard, and we only care about the fact that it finishes at some point. Sorry. Okay, so we have the intermediate stages, we have the consumer. So now we need to write the source of our data, so the source observable, and actually assemble the entire pipeline into a single one. So now what we're going to write is a method, because so far we are only creating vals that represent our async computations that, to remind once again, don't do anything by themselves until we run them as a part of our pipeline. So now we are writing our import from files method that returns a future of unit. Well, you can, yeah. I decided to return a future. We could return a task. It's just it will also show how you can convert a task into a future, so actually run it, because they both describe an async computation, but the task is lazy, so you can easily convert the task into a future. Okay, so the first thing we need to have is the files that we want to import. So we import directory is a config parameter that stores our source directory. So we are going to store it in a variable. We'll do some logging so that we see that something is happening. We can log our start time to see how long it took. And then now we're starting to assemble our entire pipeline. So we need to start with a source observable. And our starting point is a collection of files. So we're using observable from iterable. And then just pass files here. And then we want to use our transformer, so the one that combines the two others. So we're now going to use the process single file transformer with the transform method on the observable. And then, so we have the source, we have connected the intermediate transformer. Now we need to connect the consumer. So there is a consume with method that takes the consumer, the store readings one. And now this is the entire pipeline. So we combine the building blocks into a single pipeline. Now you can see that we declared our method to return a future, but the pipeline built in terms of Monix APIs returns a task. So the ultimate step here is going to, we need to call run async, which basically runs the task and returns a completable future. So we have some callbacks that we can use to check whether the pipeline completed or failed with an error. So for example, when it succeeded, we can compute the elapsed time and log it. If it failed, we receive an error, an exception that represents an error, and we can also use it for some logging purposes. So now this is the entire pipeline. We need some entry point to run it. So here there's nothing fancy here. We just load the configuration, create the repository, and then basically start the importer. And when it completes, we need to close the database connection so that the application actually finishes. So now what we have here is a Cassandra running in a Docker container. We have a collection of readings that is now empty. So we're now going to run our application. And it turns out that we are not there yet. The problem is that we want to do some async computations, but we didn't provide the thread pool, so the execution context. And actually there are two places where we didn't provide one. First one is the run async method, which is the one that converts a task into a future. And the second one is the onComplete callback on the future. They both need an execution context. And actually, this is a nice way of the compiler telling you that you should be really aware and you should really think of what thread pool you are going to use. Because even if you want to use the default one, because there is a default one in Scala, you need to be explicit about it, so you don't get a thread pool by default, because it's always good to think what kind of thread pools you're going to utilize, especially that, for example, for some I/O operations, you may need to use a different thread pool than the one used for in-memory operations, so that you don't exhaust the resources you have. So here there are two compilation errors. One says that it cannot find a scheduler. The second one, it says it can find an execution context. But actually, the Monix scheduler is an execution context because it inherits from the Scala execution context. So we can here only for the demo purposes use the default execution context from Monix, which is like the global execution context in Scala. But as I said, normally you should always consider which thread pool you need for different operations, and it may not always be the best idea to use the default one. But here we just want for it to compile, so we're going to take scheduler, implicit global. You can see that the syntax, the import is pretty similar to the global execution context in Scala. And as I said, a scheduler is actually an execution context. As well, so now the compiler should be happy. Yeah, so it compiled. We have the empty table in Cassandra, so now we can try to run it. You can see the errors that occur when some lines are invalid in the file, and now you can see that the import was finished, and actually there is some data here. So looks good. Okay, but well, there was already one place where I told you that we could try to parallelize something, and actually there is another one as well. And I start from the last one. So here, when we process the files, what we do here is actually take an observable of files, and then for each file we transform it using our transform, and then store the readings to the database. But actually, this could be parallelized because we should be able to take a number of files and process them in parallel, and then for it to happen faster in some cases. So now what we would like to do is get rid of this transform, because this is not parallelized, and try to parallelize somehow. So the pattern for parallelizing such computations in Monix is basically using buffer tumbling, so the one that groups objects into sequences, and then using flatmap. So we're going to start with buffer tumbling, the one we already used when computing the average. And here the size of the group is going to be defined by a configuration parameter called concurrent files. And then we want to flatmap. And what is going to happen in the flat map is that we are going to take a collection of files. And what we want to do is create an observable from every file and then attach our file transformer to that observable. So we'll end up with a number of observables that emit valid readings. And having the number of observables with valid readings, we're going to merge them into a single one so that the readings are emitted downstream one by one. So we're going to start by taking each file and then converting the file into an observable instantly. And this is what the observable now method can be used for. So it basically takes the item and gives you an observable that emits this item. And now we're going to use the familiar transform method to attach our process single file transformer. Because of course we got rid of the transform invocation here, but we still want to use our transformer, but we want to use it in a parallel fashion. So we have an observable here. And if we look at the type, this is actually a sequence of observables because we took a sequence of files, every file was mapped into an observable, so we end up with a sequence of observables. So what we want to do now is transform the sequence of observables into a single observable. And actually there is a built-in method for that, which is called observable merge. And it takes a number of observables and basically merges them into a single one. So we take our readings and we say that it should be treated as a collection, and that's it. So once again, what we did was taking every file, mapping it into an observable with observable now, applying our transformer, and then we ended up with a collection of observables, and using this collection of observables, we created a single observable. So this was the first place where we could apply some optimizations, and here is the second one. So you may remember that what we were lacking was an ordered version of the map async. So let's try to implement one ourselves. We're going to implement it in this companion object, and it will be called map async ordered. So its signature is going to be similar to the one of map async. So it has two type parameters. It takes the parallelism level of as the first parameter, which is an int. And it takes a function that converts the value of type A into a task of type B. So this is the description of the async computation that transforms A into B. And what we want back is a transformer that transforms from A to B, so we can use it as part of our pipeline. So the approach would be pretty similar here, but we'll start a bit different. So we'll start by taking the items of type A, and then apply the computation, so apply the task to them with map. So basically, we are applying our function f that takes the item of type A and maps it into a task, so into the description of the computation. And now it's going to look familiar because we are once again going to use buffer tumbling to group the tasks into groups of a given size defined by the parallelism. And then we're going to use flat map, but this time we will be operating on tasks. And we're going to use a built-in method called task gather. And what task gather does, it takes a number of tasks and waits for their completion and converts them into a single task. So this is like future sequence or traversable in general. This is actually very similar to future sequence. And we have our gathered tasks here. Now if you look at the type, this is a task of sequence of items of type B, and what we want back is an observable of type B. So we can pretty easily transform it into one. So we'll start with transforming our task, the bigger one, into an observable using observable from task. And now what we actually need to do is just use flat map to convert the sequence of observables into a single observable. So we can use observable from iterable here. And now we can just apply some syntax sugar here, so an implicit class that lets us use the map async as a part of our pipeline. So we can just say map async ordered here, and we provide the non-IO parallelism and the parse line method. So once again, this was the way to parallelize the initially not parallel computation. Okay, so that was for the live demo. There is certainly something more to Monix. There are some built-in consumers. There is support for multicasting, so connecting multiple consumers to a single observable. There is documentation. Actually, Monix 3.0 is just around the corner. It's still a release candidate, so I give you a link to the 2.0 version, but 3.0 will be there soon. If you want to compare it to Akka Streams, I actually wrote a blog series comparing those two, so you can have a look there. There will be a second link at the end, so you don't need to write it down now. If you're not aware of Scala Times yet, please go to scalatimes.com and subscribe to our newsletter. Here you have a QR code to a landing page with all the resources, so the source code, the link to my blog entry. This is actually the link that is beneath. And I'm actually out of time, so if you have any questions, please just catch me after the conference, after the talk, well, not after the conference. Thanks for your attention.